Hey everybody, in this AP Chem series video, we're going to take a look at pH and something called the auto-ionization of water. Remember that we've already seen some stuff with acids and bases, like the definition given by Arrhenius, which says that acids produce H plus ions in water while bases produce hydroxide ions, like this MgOH2. That's a good example of an Arrhenius base. The more inclusive Bronsted-Lowry theory says that acids are actually proton donors while bases are proton acceptors, like this HNO3 nitric acid that donates an H plus to water, making H3O plus ions and therefore acidifying the solution. Now we can go one step further and take a look at a good numerical way to keep track of just how acidic your solution is. I'm talking, of course, about pH. So a good definition we can start off with is simply saying that the pH scale is used to specify whether a solution is acidic or alkaline. At 25 degrees Celsius, it goes from 0 to 14, as most of you probably already know, where 0 to 7 indicates an acidic solution, 7 to 14 indicating an alkaline or basic one. Here's a nice chart of that scale with some common familiar substances and where they approximately fall on the scale. If you've ever wondered what pH stands for, it's power or potential of hydrogen ions. That's why the H is capitalized for the symbol of hydrogen, since it's technically measuring that. It measures how many H pluses, or more accurately, how many H3O plus ions are in the solution. The more H3O pluses you have, the more acidic your solution is, the lower the pH comes out to be. The opposite is true if there's less H3O plus ions. And lastly, this is a logarithmic scale, which means that if you're comparing, say, vinegar and lemon juice with very similar pHs of 3 and 2 respectively, it might seem like they have similar acidities, but in fact, the lemon juice is 10 times more acidic. You can see the amount of H3O plus ions that would be in each solution. This list makes up a bunch of the key ideas for this video. Make sure to pause and take some time to write those down. Now let's get into some of the math and equations behind pH, starting with something unique that water molecules can do. Water molecules can actually react with themselves. It's a weird thing to imagine. Let's take a look at the chemical equation to get a sense of the process. You can see here the two reactants are both water, where one donates an H plus ion to the other. This produces, of course, an H3O plus and OH minus in equal quantities. Notice the reversible arrow. That means this reaction reaches an equilibrium that's going to control the amount of H3O plus and OH minus in any aqueous system, including, of course, acids and bases. The equilibrium expression for this would, of course, be H3O plus times OH minus concentrations. The subscript of W on the K simply stands for water. This would have a value, so an equilibrium constant of 1 times 10 to the minus 14 at 25 degrees Celsius. Why does this matter? Well, it tells us lots of really important things. The first thing it tells us is that any aqueous acid or base is always going to have some H3O plus and some OH minus. That's because this is reversible and the reaction is always taking place in both directions. It also tells us that these two quantities are inversely related. If they both have to multiply to equal 1 times 10 to the minus 14, the more H3O plus there is, means there has to be less OH minus, or vice versa, to account for that. The final conclusion here is that we can identify acidic solutions now must be ones where if the H3O plus is higher, the OH minus is going to be lower. That's one way to identify whether a solution is acidic or basic. A basic solution would, of course, be the opposite, where the OH minus is greater, forcing the H3O plus to be lower. These make up some really important key ideas. Make sure to take some time and write them down. Let's close the video by looking at pH and how to calculate it specifically. You're going to do that by simply taking the negative log of that H3O plus concentration. There's two ways to write the formula: negative log of H3O plus or negative log of H plus. Both are acceptable, but we're going to try to stick with the first one because it's a little more accurate. Why would you do this? No reason really, other than to simplify some otherwise scary looking numbers. It's also faster to tell whether the solution is acidic or basic. For example, if we knew that a solution had an H3O plus of 1 times 10 to the minus 4 m, it's kind of tough and takes some work to use that to tell if my solution is acidic or basic. However, if I take the negative log of it, I get a pH of simply 4, and I can immediately see that this is an acidic solution. Or 1 times 10 to the minus 9 would give me a pH of 9, and I know that my solution is alkaline, or 3.32 times 10 to the minus 12 gets me a pH of 11.48. And again, I can see that my solution is very alkaline. It's just a much faster, simpler way to do it. There's one other pattern here that can be helpful on AP exams. I want to point it out if you haven't noticed it already. It has to do with the pH value being the same as or close to the exponent, the absolute value of the exponent to be exact, in the H3O plus concentration. Notice that the pH is equal to the exact absolute value of that exponent if the number in the scientific notation is 1. You saw that in my first two examples. If the number in your H3O plus concentration is not 1, then the pH will be similar to the exponent, but technically the absolute value of that exponent minus a value of 1. You can see here the exponent was negative 12. My pH then starts with 1 less than that, 11, with some decimal. It's going to be very helpful, especially on multiple choice questions, and these make up the final key ideas of this video. Make sure to pause, take some time, and write them down. That also wraps it up for this video on pH. Thanks a lot for watching, and here is a brief summary.